After studying this module, you should be able to know about the zintl phases and their structural features. Wade-Mingo rules to elucidate the structures of zintl phases. Chevrel phases and their structures. Let's introduce ourselves with this. The polyanions are well known in the literature, which was observed by the change in characteristic blue color of the sodium ammonia solution on addition of an external metal. Zintl and co-workers were able to identify the composition of a large number of such compounds containing negatively charged main group metals and semi-metals. These were the first examples of compounds having metals in negative oxidation state. The zintl clusters or zintl phases are intermetallic compounds that are named after Edward Zintl, who pioneered the exploration and structural rationale of such type of compounds. Zintl phases are not alloys. The main characteristics of zintl clusters are: number one, that they consist of an alkali, all alkaline earth metal, and a p block element or elements, which can be a metal, semi-metal, or a small gap semiconductor. Number two, they are closed shell compounds which are electronically balanced such that the number of electrons needed for covalent bonding in the structure is equal to the total number of electrons provided by the constituent elements. Number three, they are semiconductors or poor conductors. Number four, they are either diamagnetic or possess very weak temperature independent paramagnetism. Basically, zintl clusters are intermetallic compounds that are combination of elements with very different electronegativity. That is, they are very electropositive alkali or alkaline earth metals and the post-transition elements. Now, since alkali or alkaline earth metals are strongly reducing and form zintl phases, which contain the alkali metal cation together with a reduced complex anionic species. Therefore, group 1 zintl phases are ionic compounds where there is an electron transfer from the alkali metal atom to the p block atomic cluster to form polyanion. These anions in these compounds are referred to as the zintl anion, having a complete octet of valence electrons and are polymeric in nature. The cations are located within the anionic lattice. Depending upon the extent of reduction, the polyanionic structures of metals have wide range of structures such as 3D extended networks to 2D layers, two-dimensional infinite chains, discrete polyanionic cages, and intercalated compounds. These polyanions remain in solution and some of them have been isolated for structural characterizations. For example, the group 14 elements form compounds of stoichiometry M4A4 and M4A9 such as K4GE4 and CS4GE9. CS4GE9 cluster consists of a monocapped square antiprismatic G4 with 9- charge anion. The group 13 element form compounds like Rb2-IN3 and Ka containing IN6 octahedra and Ga8 polyhedral anions respectively. The group 13 elements also form compounds such as aluminium 5 CuSi3, RbGa7 and K3Ga13. The compounds like CS 5 Bi4 contain tetrameric chains of stoichiometry. B form 4 minus ion. Moreover, the zintl clusters obtained from group 1 cations such as Na96, In91, M2 and Na172, In192, M2, where M can be nickel, palladium or platinum, display fullerene shaped structures. The fullerene type cages in these phases comprises of pentagonal and hexagonal faces with one sodium atom per phase of the fullerene. In the nickel-centered clusters of the formula K10, I10, Ni, the nickel atoms are found inside the indium spheres. Therefore, the formula of such type of intercalated compound is written as nickel at In10 at Na36 at In74, where the symbol at is used for within. Some of the structures are given here. An extremely interesting example is that of the encapsulation of iron atom inside a pentagonal prismatic zintl ion with the formula FeGe10 with 3 minus charge, the structure of which is shown at present. A large number of intercalated metal polyanions have been known which have been structurally characterized in detail. One more interesting example of two clusters Na96, In97, Ni2 and Na96, In96, the stoichiometry of the two clusters have negligible difference of 2 additional nickel atom per 200 atoms of sodium and indium, but the structures of the two compounds have nothing in common. The nickel containing cluster is fullerene shaped, whereas the other one is diamond shaped. Let's study the group 14 zintl ions such as germides, stenides and plumides. Unlike carbon and silicon, the group 14 elements such as germanium, tin and lead do not form binary compounds with metals. These metals instead form zintl phases and zintl anions, which consist of clusters of these metal atoms. Some of diamagnetic zintl ions of this group are Ge9 with 2 minus charge, Ge10 with 2 minus charge, Sn8Tl with 3 minus charge, Sn9Tl with 3 minus charge and Pb2 Sb2 with 2 minus charge, whereas the Ge9 3 minus charge and Sn9 3 minus are exemplified as paramagnetic. The general synthetic route to achieve zintl phases is by the reduction of germanium, tin and lead in solution of sodium in liquid ammonia. As you can see in this reaction, tin gives you sodium Sn 1.0 to 1.7 in presence of sodium in liquid ammonia. Let's study about the Wade's rule now to elucidate the structure of zintl phases. Wade's rule were developed to define the structures of borane clusters where a BH unit contributes 2 electrons to the cluster bonding. In zintl phases, there exists a well-defined relationship between chemical and electronic structure which can be explained by applying Wade's rule. Number 1. In each group 13, 14 and 15, atom contributes 1, 2 or 3 electrons to cluster bonding. Thus, in polyanionic cluster, where gallium, indium and thallium vertices contribute 1 skeletal electron, where silicon, germanium, tin and lead atoms contribute 2 electrons, whereas arsenic, antimony and bismuth units provide 3 electrons to the cluster. On similar lines, the selenium and tellurium provide 4 skeletal electrons. Thus, silicon, germanium, tin and lead atoms can mimic a BH unit. It can be said that each group 14 element is isolobal with BH-1 unit. Similarly, the arsenic, antimony and bismuth vertices are isoelectronic with CH vertices. Third point, the post-transition metals make use of a 4-orbital sp3 valence orbitals set, assuming that the inner shell d orbitals are not involved in bonding but instead comprise non-bonding lone pair of electrons. Some simple examples of homonuclear where ionic post-transition metal clusters are mentioned as number 1, square shaped. In bismuth 4 -2 ion, selenium 4 2+ ion and tellurium 4 2+ ion, they all have 14 skeletal electrons. For example, in bismuth 4 2- 4 into 3 plus 2 gives you 14. That is, the 14 electron can correspond to 8 electrons for the 4 sigma bonds and 4 electrons to the 2 pi bonds, whereas remaining 2 electrons constitute the 2 formal charges. Hence, the structures of these polyanions are isoelectronic and isolobal with the delocalized planar cyclobutadiene dianion. Butterfly shaped structure. In Tl2, the skeletal electron counts is 12. Hence, the structure consists of 4 sigma bond and 2 pi bonds, isoelectronic and isolobal with neutral cyclobutadiene. However, the structure undergoes a John Taylor type distortion at one of the 4 vertices, leading to a butterfly structure. Tetrahedral structure. For example, SN2 Bi2 2- and Pp2 Sb2 2- have 12 skeletal electrons, which is isoelectronic with a tetrahedron analogous to P4. Trigonal bipyramidal. SN5 2-, Pp5 2- and Bi5 3+, all have 12 skeletal electrons to make it analogous to trigonal bipyramidal structure like that of a C2B3H5 carborane. 7 vertex structure. AS7 3- and SB7 3- have a different kind of skeletal electron count. For example, 4 into 3 plus 3 into 1 plus 3 is equal to 18 for 7 edges with 3 vertices of degree 3 bonds and 3 vertices of degree 2, that is 2 bonds. Next is bicapped square antiprism. PB10 2- has the 10 into 2 plus 2, that is 22, with a formula 2n plus 2 with n is equal to 10. A 10 vertex structure is a D4D datahedron analogous to the B10H10 2-. TLSN9 3- is isoelectronic with PB10 2- and has similar structure. Let's study about the Chevrel phases. Chevrel phases are an important class of material displaying spectacular physical and chemical properties such as high temperature superconductance up to 14 to 15 degree Kelvin, extraordinary electrical and magnetic property, remarkably high fields at a temperature 0. The general formula of clusters containing several phases is MX, MO6, X8, where M can be a monovalent, divalent or trivalent element where X can vary from 0 to 4. The X is a chalcogenide anion, which are sulfur, selenium and tellurium, which can be substituted by a halogen or an oxygen anion. The main cation, molybdenum, can also be sometimes replaced by another transition metals like Nb, Ta, Re, W and others. The remarkable chemical and physical are closely related to the structural features of these clusters, such as hosting a large number of external elements into the crystal structure. Let's study about the structures of Chevrel phases. The metal clusters of formula Mx, Mo6, X8 are known as Chevrel phases. These are the first compounds possessing high temperature, superconductivity and high crystal fields. A common feature of the structure of these clusters compounds is a Mo6 octahedron consisting of 6 tightly packed molybdenum atoms. The molybdenum distance is in the range of 2.67 to 2.78 angstrom. Each face of the octahedron is capped by a sulfur atom forming a S8 cube around the Mo6 octahedron. Thus, there is a Mo6 octahedron within a S8 cube, as you can see here. Thus, each X atom forms a nearly perfect cube encapsulating a molybdenum octahedron. Moreover, this Mo6X8 unit is contained within a larger cube of M atoms in such a way that all the three polyhedrons share a common threefold rotational axis. In the real situation, the two inner polyhedra are rotated about a common threefold axis. For example, in the PbMO6S8, the inner two polyhedral are turned at an angle of 25 degree. In the Chevrel phases, each M atom is coordinated with X atoms cubically with 2 short and 6 longer metal X bonds. Hence, each X atom is tetrahedrally coordinated by 3 molybdenum atoms and 1 metal atom. Let's summarize what we have studied. That metal clusters are an important class of compounds displaying interesting physical and chemical properties. Among these, the zintl and Chevrel phases are unique class of metal clusters. Zintl phases consist of an alkali or alkaline earth metal and a p-block element or elements which can be a metal, semi-metal or a small gap semiconductor. Group 1 zintl phases are ionic compounds where there is an electron transfer from the alkali metal atom to a p-block atomic cluster to form a polyanion. These polyanionic structures of metals have a wide range of structures such as 3D extended networks to 2D layers, two-dimensional infinite chains, discrete polyanionic cages and intercalated compounds. The zintl clusters are commonly synthesized by the reduction of germanium, tin and lead in solution of sodium in liquid ammonia. Taking advantage of the relationship between chemical and electronic structure of the zintl phases, Vedde and Mingo rules can be applied to elucidate the structural features. The Chevrel phases are an important class of materials displaying spectacular physical and chemical properties such as high temperature, superconductance, extraordinary electrical and magnetic property, remarkably high fields at zero temperature. The types of reactions that cluster complexes undergoes are reactions with electrophiles and nucleophiles, oxidative addition reaction, and reactions on metal-metal multiple bonds.